Hello IB, we're going to have a look now at the derivatives of trig functions. So in this case we're going to go back to the unit circle and look at our point going around the circle, around the unit circle. So remember your derivative functions, the rule that we use to find the gradient or slope at any point on a function. The slope's a rate or a change in y per x. So we're looking at our unit circle, and what we're going to do is consider our point P, which we have on our unit circle here, and we're going to say it's moving around the circle at 1 unit per second. Remember, our coordinates of P are determined by the angle, and the x coordinate was by cos theta, so whereabouts is the x value for this, and our y coordinate is the same as sine theta. And remember how when we looked at the unit circle, we could come up, it's already going here, we could come up with what the graph looks like. So let's just go restart with this. So this is the y value. See how it's taking the y value in each case? That leads to the sine curve. Now it's looking at the x value, if you can see that quickly. Then it comes up with this curve, which when we bring it round onto the axis here, it gives us the cos curve for the x coordinate, and we notice that there's a pi on 2 phase change between the two of them. So if we look at the speed of P, then that can be described in terms of its angle or the length of the arc from the starting point. So our point, we said, was going around at 1 unit as a linear speed. Up here we said 1 unit per second as a linear speed. So that way we can say that the linear velocity of the point is the rate of change of the arc length with respect to time, dl dt. So dl, the change in the length of the arc with respect to time as our point goes around the circle. We could also talk about the speed of the point in terms of its angular velocity, how much the angle is changing over time. So this is the rate of change of that angle AOP, which is our theta here, with respect to time. So we could describe it as d theta dt. So here we've got two rates. We're talking about derivatives. One's related to the linear speed, one's related to the angle. And we said our linear speed here, dl dt, was going to be 1 unit per second. And remember, the length of our arc is related by theta and the radius. So L is equal to theta times r. So because r is equal to 1, then our d theta dt will also be 1 per second, but our 1 refers to 1 radian. So here is our units, 1 radian per second. So let's say our point is going round at that speed of 1 unit per second or 1 radian per second. How long will it take for the point to go through 1 full revolution? If it does 1 unit every second, so there's our 1 unit, because our unit circle is 1 for each of the radii, and this theta, that's going to be our 1 radian. Remember we use that 1 with the little c for the notation. So if that does 1 unit per second, then how long does it take to do a full revolution? Obviously 2 pi, because there's 2 pi radius. Like, so we either go circumference is 2 pi r, our radius is 1, and it does that much in, and we're doing 1 radius per second, so therefore it'll take 2 pi seconds to do the full radius. Anyway, so that's just starting to talk about velocity and the point moving. So let's come back to our graph and let's think about the derivative function just in terms of the graph. So now, remember our sine x was the y coordinate. So we can see that the y coordinate is starting off at 0 for our point on the circle. Then it reaches 1 when it's at, remember, at pi on 2 when it's at 90 degrees. Then it comes back to 0 and then goes to -1 when it's at 3 pi on 2, then back here at 2 pi. So the question is, when is its speed 0 and when is it a maximum? So if you think of the point going around the circle, and this is the y coordinate, so in terms of the y, it's going up, turning around, then coming back down, and then turning around and coming back up again. So when it turns around at this point, it has a horizontal tangent on our original function. So do you remember what that told us? If it's got a horizontal tangent, the tangent's there, that's a point where the velocity or the tangent, the slope of that is 0. So the slope of that graph is 0. So now if I draw on here my tangent function at this point, so if I do f dash x here on the same graph, so at this point we have a 0 tangent, gradient of the tangent, so the derivative function is 0. Also down here it's 0. Also over here it's 0. When you think the steepest tangent is, here it's 0, and we can see the tangents there and getting really steep, and then it's not as steep up here. So it's going from a little bit steep to really steep, back to not so steep, and then 0 again at this maximum. So basically it's going from, this is a positive gradient, so it's getting very steep, and we just don't know how high, but in fact it goes up here. Then it comes not so steep back down to 0. All right, now at this point, I'll hold it, back to front, hold it, let me fix this up. All right, try again. Here it's 0, and in this region here we have a negative gradient. So it's a little bit negative, then getting more negative. So it's coming down, negative gradient, and then not maximum, then not so negative, back to a 0. Now it's a positive gradient. So, oh, it's a funny looking curve. So it's coming down like that. So see how it looks like the sine curve, but it's not, it's a different phase. It's not lined up exactly. So this graph looks like our cos curve. So when we've got the derivative, when we have y equal to sine x, then our dy dx, let me line that, get it ready for you. All right, I've now got it set up. It looks like our cos graph, and so if I put that on here, we can see it sort of follows my rough drawing. So in other words, the derivative of sine x is cos x. Cos x. Let's now look at the next one. All right. So here's our cos x, that's the x coordinate. So if we think of the point going around the unit circle, and we're looking at the x coordinate now, so it starts off here at 1, then it comes closer to the origin here, so the distance is 0, and then it heads over to -1. At this point, wherever we reach a maximum, our derivative is going to be 0 because the gradient is 0. Gradient of the tangent is 0. So our derivative function will be 0, 0, another 0 here at 2 pi. This is at pi. So that should be over here a little bit. The gradient here means it's a negative gradient. It's heading in the negative direction. So we'll spend a lot more time working on this later. So here, if this has got a negative slope, that means our curve is coming down this way. Now, after this point, we are in a positive slope. So our derivative function, f dash x, is what I'm plotting in blue, comes up and then down for 0 again here. So this graph, it looks like a sine curve, but is it a sine curve? Not exactly. What's the difference? It looks like it's being reflected. So that means in here we need a negative. So now if we plot this, it will line up. So in other words, the derivative of cos x equals minus sine x. So the derivative of sine x is cos x. They're both positive, but the derivative of cos x is minus sine x. And we can see this with this applet. This applet you can get from the textbook. So here we've got sine x, or in this case sine t. So there's the gradient. We can see the tangent is now positive, 0, negative, 0, positive again. If we look at, so there's our sine theta or sine t, and our derivative function is positive cos t. Let's now plot cos t. So there's our original function, and now let's get the derivative. If we follow the tangent around, here it is up at 0, negative, 0, positive. So here we've got a negative gradient corresponding to this, the 0 gradient at the maximum corresponding to that point. All in between here is in here between is the positive gradient, so that's all matching here. All right. So there's our cos graph and minus sine graph. Tan x. So what's the derivative of tan x? It's going to leave you to have a go at working that out. We haven't got that, and we could look at the graph and try and guess it from there. But let's remember that tan x is sine x on cos x. And if you want to differentiate that, you can use your quotient rule. So what I'd like you to do is pause it, quotient rule, and see what you come up with. Meanwhile, I'll tidy up this writing. So stop, pause the video, and do the derivative using your quotient rule. How did you go? Did you come up with a derivative function? So hopefully you came up with 1 over cos squared x. That's also the same as sec squared x. It's another terminology for the reciprocal function of 1 over cos x. So what does that look like? So if we come to our graph of cos x, so that's cos x, starts at 1, goes down and up. What would 1 over cos x look like? So we want to basically square this, which means it's always going to be positive, and then take the reciprocal. So the first thing is, remember our denominator can never equal 0, so that means we can never have cos x equal to 0. So wherever cos x is 0, we're going to have an asymptote. So down here, when does cos x equal 0? At pi on 2, because it's like your x-coordinate. So that's at pi on 2. And here it's 0 again. That will be at 3 pi on 2. So that's 3 pi on 2. Then, when it's 1, if you do 1 squared, is 1 over 1. So this point is going to match. That one's going to match. Minus 1 here. When you square minus 1, you get 1. And the reciprocal of 1 is 1. So this point here at pi will also be here. And then in between, we basically have a smooth curve from, as these numbers get smaller, our fraction gets bigger. So this is our curve coming down here, touches there, then goes back up. It's really weird drawing on this. Here's our next asymptote down here. And our curve will look like this again. Touch there, then back up again. So that's the derivative function. All right, I've drawn that up here, so it looks a bit neater. So there's our tan function, and this is the 1 over cos squared function. So that's what I've plotted on here. You see that all joined up. So the asymptote we talked about coming down here at pi on 2, and at 3 pi on 2, so pi later. All right. So now let's look at some other applications of this. If we have a function inside our sine, remember your chain rule. So think chain rule. So the derivative of sine of f of x becomes cos f of x. So leave the inside the same, just differentiate the outside, but then multiply by the derivative of the inside. Then this one, cos of f of x, derivative of cos x becomes minus sine of our function. Leave the inside alone, just differentiate the outside part. Then the inside part gets differentiated to f dash x. Tan f of x, remember that becomes 1 over cos squared f of x, whatever we've got in our function, times the derivative of the inside function. And that could end up the top here. All right, so chain rule works the same. Here we've got x times sine x, so we've got a product rule. So we're just going to go, remember our u, v, u equals x, u dash will equal 1, v equals sine x, v dash equals cos x. Pause the video and have a go. Okay, so just substituting in there, we get 1 times sine x plus x times cos x. You can't do much more to tidy that up. The next one here, we can see we've got a tan, it's being squared, and we've got a function inside. So there's nothing being multiplied there, so it's not a product rule. It's basically a chain and a chain rule. So like a double chain rule. So dy dx equals, put down the 4 and leave it. Now think of that as 4 when you've got tan of 3x all squared. So do the outside first. Down comes the 2. So we get 4 times 2 times tan of 3x. That's like to the 1. Now differentiate tan x, and that gives us, equals. So that'll be now times 1 over cos squared 3x. And now differentiate the 3x times 3. We'll put that 3 over 1. So now, putting all our numbers together, 4 times 2 is 8, times 3 is 24. This is in the numerator, that's in the denominator. So we end up with tan of 3x over cos squared x. It's cos squared 3x. All right. This one here, these are all just different examples of, in this case, a chain rule, because you've got a function in a function. So chain rule, another chain rule, you've got a cos x inside a cos x. And here, again, you can rewrite that as a chain rule. So your first one, so y dash will equal, differentiate sine, you get cos. Leave the inside the same, then multiplied by the derivative of the inside. So careful when you're writing that you make it clear what's inside the cos and what isn't. So you'll often see that written with the 2x out the front. Oops. So cos x squared. So pause the video and have a go at those ones. So I'll put them up here. These are some the solutions for the other ones. You can have a look through and we can have a look at those in class. The next one last one to show you here was when you've got a chain rule here, you want to differentiate that, but you want to find the gradient of the tangent at a particular point. In other words, you're trying to find f dash at 2 pi on 3. So you need to differentiate it first to get your derivative function. So you'll have 3 sine squared x times the derivative of sine x is cos x, and then substitute it in. So 2 pi over 3. So substitute in sine of 2 pi on 3, and that needs to be all squared, times cos of 2 pi on 3, and of course you're then going to need your triangles to work that one out. Alright, so remember in this case a 60-30 triangle. Sixty, 30, 1, 2, root 3. Where's 2 pi on 3? That's going to be 60 degrees in the second quadrant. So 3 lots of sine of 60 is going to be root 3 over 2. In the second quadrant, that's positive, times the cos of 2 pi and 3. So that'll be, cos is a half. And in this case, because it's quadrant 2, it'll be negative. So we get 3 times 3 over 4 times minus a half, and we're left with minus 9 on 8. All right. Anyway, thanks for listening, and we'll see you when we can in class.